Welcome to Unit 6. Our focus in this unit will be on the very foundations of statistical inference. You might recall that in Unit 1, we did discuss two major branches or aspects of statistics, namely descriptive statistics and secondly, in statistical inference. In statistical inference, our actual goal is to study different population characteristics using sample information. How do we go about doing that? Let us take an example. On page 2 of our notes, we're going to start off with the idea of what point estimates are and see how such point estimates vary from one sample to another. To drive this discussion, let's consider this motivating thought. What do you think? What is the population or the percentage or proportion of American adults who support the expansion of solar energy? 80%? 54%? Well, we can go on with that what? Guess. In statistics, in order to use data to drive decision making or arrive at an informed value or an educated value of what this unknown population characteristic is, we collect data about the target population, which brings us to the question, what is the target population as far as this research question is concerned? Well, that would be all American adults, because this question concerns all American adults, and regarding this population, we're interested in a characteristic of interest, which is otherwise known as the unknown parameter, and that would be the percentage or proportion of this population, all American adults who support the expansion of solar energy, the expansion of solar energy. Now, how are we going to figure out what this percentage is? First of all, let that unknown percentage, let it be represented by the letter P. And in this case, P, that proportion or percentage is unknown. If we are able to reach the entire population of all American adults and they truthfully and willingly express their true opinions, it is possible that we might find that 88% of them support what? The expansion of solar energy. Well, that is possible, but is it practical? Reaching all American adults can be a little bit what of a stretch. And so an alternative route that statisticians take is to conduct a survey or a poll where they will take a sample of a number of American adults, ask them this question, do you support the expansion of solar energy? And let's say that in that poll or that sample chosen from this population, the population of all American adults, let's say that 1,000 individuals were taken and asked questions on this topic. Well, what do you think? Do you think from that 1,000, exactly 880, representing 88% of those in that sample, will exactly say that they support the expansion of solar energy? I would bet that if that is the case, that must be some serious luck. In other words, the proportion of those who support the expansion of solar energy can vary from one sample of 1,000 American adults to another. So it means that we can go to the sample of a particular size of interest, say 1,000 in this case, and it is possible that the sample proportion, which we represent as P with a hat on top, or P bar, one of them, anyone is acceptable. This can vary from one sample of 1,000 American adults to another. Let us say the first 1,000 American adults who were polled on this topic was such that 85% of them say they support the expansion of solar energy. Take note that because this 85% pertains to a sample, based on what we learned in Unit 1, this is an example of a sample statistic. So this is an example of a sample statistic. And one thing is definitely worth noting, and that is that P at, the sample proportion, varies from one sample of 1,000 American adults to another. So it varies from one sample to another. This phenomenon, this occurrence that the sample proportion of those who support the expansion of solar energy will vary from 1,000 American adults to another sample of 1,000 American adults is known as sampling variability. And so this, I'm going to cap it here and say this is what sampling variability. It will vary from one sample of 1,000 adults to another. Well, if it varies from one sample to another, which value are we going to settle for? In other words, we are operating in an uncertain territory here. So you see, if the true proportion is 88%, which we might not know exactly what it is, most times than not, we don't know what this exact proportion is unless we access the entire population. But we're trying to rely on our best estimate from the sample. So this number, the sample proportion, coming from the sample, is called a point estimate. And that helps us to define something called sampling error. Error not in the sense of a mistake, but error in the sense of deviation from the actual value. In other words, if all we had was this sample response of 1,000 American adults, then what we get from that sample is a sample proportion called what, P at or P bar, and how far is it from the actual unknown, because that is what we really seek to know. This expression, the difference between what you estimated from the sample minus the actual value, is known as sampling error for a particular sample. In general, it is the value of the sample statistic, whatever information you are able to pull from your sample. How far is it away from the actual unknown that you want to find, namely the population parameter? In this context, if we wanted to speak in numerical values, well, if we got 85% from this population, that is 0.85, minus what it is actually if we had all the resources in the world to access the entire population, and that will give us negative 0.03. This is the sampling error for this particular sample statistic. Remember, this value, that is the sample proportion, will vary from one sample to another, which means by extension, the sampling error will also vary from one sample to another. In other words, your P at is a random variable. It is a random variable, like we learned earlier in earlier classes. And if it's a random variable, we're usually interested in the mean of that random variable. So it has with a mean of expected value of that random variable, otherwise called the mean of that random variable. It will average around what? The actual population parameter we want to estimate. This is an important formula for you to note. And then another thing is we'd like to also talk about the standard deviation of this random variable of P at. This is otherwise written as sigma of P at. It is given by the formula P into 1 minus P all over N. That is the second formula. Well, there are conditions attached to the use of these formulas. This is provided that our n times p is greater than or equal to 10, and our n times 1 minus p is also greater than or equal to 10. These are thresholds, or I mean, the 10 is a threshold that guarantees that if this conditions hold, then our p at follows a normal distribution with a mean of p and a standard deviation of the square root of p into 1 minus p all over n. So, as a rule of thumb, provided these conditions are satisfied, that is n times p, the total number in the sample, times the population proportion, or the sample proportion if it exceeds 10, and the same goes with n times 1 minus p, then we can claim that the sample proportion, even though it varies, it will vary according to the distribution known as the normal distribution, which we discussed in earlier chapters. So, in the next video, we're going to begin working with these formulas to be able to compute probabilities associated with the sample proportion.